Right, so here's the recap of this week's lecture. The whole purpose of the lecture is to find out a little bit more about the evolution of the ISA of the MIPS 32 and to see that things do change when it comes to the architecture of a processor. And then we're gonna get 2-3 examples going from high-level languages to the MIPS as an example. First things first here, the latest version of the MIPS is number 6. Where is it? No, voila. So it's release number 6, right? It dates back from 2014, and you have the official documentation that I usually advise checking out at least. It's available on the internet for free for sure by the MIPS people with a legal copy. Right. However, don't worry about it. The things that you'll be using, and I guess you already started using it during the labs or the tutorials. I don't remember anymore. It's the Mars simulator, and you're gonna notice that the Mars simulator does not implement the latest version of MIPS. However, it does implement something that is extremely useful, and you'll be, practicing using the instructions that are available over there. All right. So this is a quick recap of the things that we talked about in last week's lecture. So the different registers that are available in the MIPS for the MIPS, and this is part of the architecture. So the MIPS people decided that they want to use 32 general purpose registers, and one of the registers is hardwired to the value 0 because they've noticed that the value 0 is something that is extremely common and it's extremely needed, so it should make things faster for everyone. Then per convention, so theoretically and in practice as well, any register could be used to store anything, purely theoretical. And you can, it's feasible, even in practice it's feasible. However, there's a convention saying that this register will be reserved for the assembler. Those registers should be used for return values, for instance, and those registers are arguments for functions. Those are temps. Some of them are save, and then you have things that should be used by the kernel. So the people who will work on developing a kernel that is meant to work with the MIPS architecture, for instance, they should know that these are the registers that they should use, although they can use any other register in order to become conformist with, or to conform with the convention here. We should try and respect as much as we can this particular convention. So there's a special purpose register with MIPS that is not visibly visible from an architectural point of view, and this is something that we cannot program ourselves directly. We don't have direct access to it. However, there are some instructions that will lead to changing the value of the PC. So there's a general idea that if we're doing the normal classical sequential programming, the PC will hold a value, and then some instructions will alter that particular flow of instructions, and then we're gonna have a different value in the PC register. So most of your colleagues in the face-to-face lectures, they guessed it correctly. They already knew what the PC register is all about. And to make a long story short, it contains the address of the next instruction that should be executed. Right, so here we're looking at the 32 registers, and each register is 32 bit wide or long, doesn't really matter, depends how we look at it. And then we are seeing the special purpose register here, right, the PC, and apparently we used to have 2 special purpose registers as well in the older versions of the MIPS ISA, but it's not there anymore. And these are the high and low registers. Now the question is, why would the MIPS people decide, why would they decide to create two special purpose registers and call them high and low? A possible answer would be, and this is the correct one, maybe some instructions, they will yield a result that does not fit in 32 bits here, so we will need something bigger. Hence we have those special purpose registers to represent bigger numbers, so we have the size of 2 words here instead of only 1 in those registers, in any of those registers, for instance. So here, for instance, we can have the low part of the number stored on that register, and the high part of the number, like the most significant one and the least significant one, could be stored separately in those registers. So the four most significant bytes will go on the high, and the least most significant, least significant bytes, the 4 of them, will go on the low, for instance. And in recent versions, especially the 6th, those registers are not there anymore, and we tried to figure out, we were trying to role play during class, in the sense of, we imagine ourselves as a computer architect, and we see what led to the evolution and the decision to do away with the use of those registers. So I was really impressed when one of your colleagues answered that, well, we already dispose of a bunch of registers here, and theoretically, virtually any two registers could play the role of high and low. So why bother adding extra registers here when we can use the already existing registers? So yeah, there's an alternative for those. They are intrinsic to the general purpose registers here, and we can use them. So yeah, we can do away with those, and this is exactly what the MIPS people decided to do. Right, so here, typically in your exam, I'll give you a schematic, and we're gonna try to analyze it. I don't know how many times I repeated that particular statement here, but it's still true. I cannot understress it enough. We can see the memory here, and it's organized in a grid-like manner. And you can see that we can see the small squares here, and we've said that the smallest memory unit is called something. I'm not going to remind you, you should know it by yourself today, by now. And then we can see that with your colleagues, with your face-to-face colleagues, we tried to figure out how many processors do we have in this BIC. So apparently someone guessed correctly that at least we have the CPU, and then we have the FPU, with the FPU registers, with the floating point registers that I decided that we're not going to cover in this course. You're gonna see it later in your microprocessor course, it's not a problem. Alright, so this could be seen as a coprocessor as well. So we have the main processor, a coprocessor, and another processor that we're seeing here deals with, so this one deals with floating point, and this one deals with traps and memory. And those who are taking the OS course can notice trap, what is a trap, and we'll see the relationship between what we're talking about here and the OS course. I'm not going to cover this one either in that course. All I'm gonna focus on is the main CPU of the MIPS architecture, and these are not the only coprocessors, and we're gonna see that we have up to 4 coprocessors. One of them is for the traps, so for the exceptions, for the system calls, etc. One of them is for the floating point, as we said, and then we have 2. One of them, for instance, for those who've already seen the previous video, we've seen that the MIPS was actually used in the implementation of some Nintendo console, gaming console, and there's a I would like to call it a GPU like. It's not GPU per se, but I mean it's a GPU. It has a purpose to to deal with vectors and some multimedia in the Nintendo console, so that was useful there. And then we have a fourth one that will have some functionality that I'm not even gonna cover in this course as well. So our main focus will be on the instructions that deal with this, mainly with the CPU, and maybe from time to time maybe that one, maybe. Right, so this means that the ISA, the instruction set architecture, should be divided in different sub-dictionaries. So each dictionary contains the instructions that are understood by one of the co-processors and the main processor. Fair enough. Alright, so let's see the different functional groups of the instructions. So load and store, and systematically whenever we speak of load and store, you should think about a particular hardware component that is present in a computer, and you should know it by now, so I'm not going to give it away. Computational, mathematical, logical, and jump and branch. So the jump, we've seen that type of instructions, that this one will alter the sequential flow of instructions. So we can go from instruction number 1, 2, 3 sequentially, and then jump to instruction number 10, for instance, without going through instructions 5 all the way to 9, for instance. And branch could be seen as a jump. So the jump is an unconditional one, and the branch could be something like a jump. However, it should be a jump if there's a certain condition that is true or false. So if there's a condition, well, I'm gonna go either take one path or the other, hence the branch. It looks like a tree branch. Alright, so other miscellaneous instructions, and one of the instructions that I wanted to solicitate your engineering skills about is the NUP. So what would the NUP instructions be? And this is what I asked on the face-to-face lecture, and after a hint saying that the NUP instruction could be implemented using for instance the register number 0 of the MIPS architecture, and this rang a bell when we talked about if you want to lose some time, execute some instructions to lose some time, so without having any operation that is meaningful in a way or another. So there are some no operation instructions, right? They're there for a reason, and we can see it for now as we're gonna try and lose some time, lose a couple of cycles for some reason, and we're gonna see that part in the when we're gonna tackle the implementation of the ISA. Alright, and a bunch of instructions that are meant for the coprocessors. So there should be an S for that because there are multiple coprocessors. Alright, so let's see. We have the load bytes. We've talked about it. If we wanted to check one byte out of a word from memory instead of the whole word, or if we want to get the whole word, for instance. Then you can notice here something that looks like those, but it has a NEVA. So EVA coming right after the instruction here, with an E here, for instance. And we've seen that this is enhanced virtual addressing that is especially for big kernels. So in order to be able to use the memory efficiently with big kernels, well, the MIPS people created this special type of instructions as well. And here you can see further, once more, the relationship between the kernel, which is the last layer when it comes to the logic software part of a computer, and the ISA, which could be seen as both the machine code, so the hardware part of a computer, and the interface with the software part. Right, a bunch of things here regarding the ALU, for instance, and we were surprised, rather shocked, to see that the add immediate word that you're gonna use so much in your Mars simulator, because you're not using the release number 6. The Mars is implementing an older version of the MIPS. Well, it doesn't exist anymore in the newest version, so wow, that's a shocker. Why would the MIPS people decide to do something like that? By the way, what's the size of immediate in? Can be possible. So what would be the size of the immediate part? Remember, with the add immediate, we don't have to have 2 source registers. We only need 1 source register, and we made some adjustments to the field in order to have a higher number of bits in order to represent the immediate value. So we have 16 bits to represent the immediate value. So what happened here? How come it's removed in release number 6? Well, it's extremely important. It's an extremely important instruction. Why would they remove it? So the answer lies in, if it's removed, this means that there's some kind of substitute for it, equivalent to it, and the equivalent is none but the add I with a U. So add immediate unsigned word. So for software oriented people, this is a shocker. This means that with an unsigned here, signed, unsigned. Well, unsigned means that I won't be able to represent negative numbers, for instance. Well, that's not completely true, because in hardware, unsigned does not mean the same thing. The proof, I just had a screenshot of the actual documentation in the very next slide, and we're going to see it together. So here you can see that the term unsigned, right, is kind of misleading here, because it's not about not being able to represent negative numbers, but however, this means that the instruction will not create an exception on overflow. So basically, if I'm adding 2 numbers and the result will not be able to be fit in the register, well, if I'm not using the unsigned version of the instruction, well, an exception will happen, an overflow exception will happen. However, if I'm using the unsigned version of the instruction, well, there won't be any overflow. The system will not trap on overflow. Alright, so this is a way to ignore overflow. That's it. So we can still represent negative numbers with an unsigned instruction. Right, and then a shocker with my Pikachu. Number 6, I've kept on saying that memory alignment is important, etc., and it helps a lot in speeding up, getting the words from memory. And then the MIPS people decided in release number 6, so in the release that you're not using, you're using the previous releases, they decided to do away with memory alignment. Hence, they introduced in that version, in that release, in align instruction. See, so when they removed a couple of instructions in release number 6, they made space for more instructions to be created. And you've already know that because of the different fields in an instruction, which is a fixed size instructions for or instructions. So there's a number of bits that are available to represent an instruction. Well, to make a long story short, we're gonna just check the 6 bits of the opcodes, the operation code, even though that they could be extended using different fields. But I mean, you can see that there's a limited number of bits, and we cannot like have an infinite number of instructions. We need to make space if we want to create new instructions, right? And this means that now we can go ahead and get words. They're not aligned on each line of the memory. So basically, maybe a drawing here would help. So the memory alignment the memory alignment constraint restriction dictated that a word should be on one line here, and a word is made out of 4 bytes. So word 0, word 1, word 2, etc., etc. Right? And using byte addressing, each word is 4 bytes away. Now, without memory alignment here, so all we can do is start a word here, for instance, and get the bytes here. So my word 1 will be represented by those words and not on a single line here, for instance. It could be seen logically like that for now. So in order to get a word from a bunch of 2 words that are on separate 2 lines here, well, I can get a whole word. Alright. Whoops. A bunch of things that were removed here, and apparently multiply and divide, they're all because they were removed. And if we analyze a little bit closer here, maybe I'm interested in there. So you can notice that most of those dealt with the high and low. I mean, all of them. They dealt with the high and low special purpose registers that do not exist anymore. So basically, if the registers did not exist anymore, so we're gonna remove them. Question: what would be the equivalent of those? So where are the alternatives? Well, they do not exist. So if they do not exist, we'll need to create them. And there we go. This is when in arrays number 6 here, well, we have now those versions of the multiply and divide instructions. Fair enough? Alright, so one of the last things that I showed my students were the jump and unconditional jump and the different things related to that. I mean, the different types of jumps. So I have an unconditional jump here. It means that I'm altering the flow of instructions. So if I encounter a jump here, instead of going to the very next instruction, well, I'm going to jump to whatever instruction is being represented by this value here, or let's call it label for now. Right? So I'm going to jump to the instruction that is meant to be here. Right? And that's it. I'm ignoring all the code that's between that and destination instruction and the jump instruction here. However, sometimes, and this is an example that we imagined in class, I'm in my main memory and you're doing some Java because you're Java experts, and you wanna use an object, so let's call an object dot function 1, which is the first method of the object, right? So after creating the object, I'm calling the function relative to that object in order to do something. So I'm gonna jump there. So you can notice that I'm not continuing anymore here. Go to that particular function here, execute it, and once I'm done with the function, what would happen? Well, am I going to continue to the next function there? No. I need to go back to the very next instruction in my main function here. So how can I make sure that this happens? Well, with a jump I cannot do it. So I need to do some kind of linking, some kind of linkage or linking. I wouldn't know which one to use here, but anyways, you got the picture. So the idea here is to save something and restore it to use it for later. What would be that thing that we need to save? And think about the beginning of that recap video. Something that starts with an R and ends with an A. Alright? So I'll save something here and then restore it whenever I need to continue once I'm done with the function. Alright. Alright, so here we can see a bunch of instructions regarding the exceptions, for instance, some miscellaneous instructions. It would be a good idea to see, and once again to check that these are the things that most probably the kernel will be dealing with. Alright, so that's it for that part. The third type of instructions in the previous lecture was called jump and link, and it has an X. Could be interesting to research that because I spent some time during the lecture trying to figure out what that is with the students, and I told them that sometimes in the exams, most of the times in my exams, I ask questions that are challenging, that will require their experience in the course. There's no parroting in my exams. There's no copy paste. So I will introduce an instruction and I will let them explain it in a way or another. That could be one example. And in order to find out what the jump and link X means, X stands for exchange, we said that there are MIPS architecture that are meant to be with 16-bit operands, some of them with 32, and this is what you're dealing with, and some of them with 64. So you can see that we have different modes of the ISA. So what would the exchange be here? So the exchange maybe means that I'm going to somewhere in my code where I'm not dealing with that version, but I'm dealing with that version or something like that. So go ahead and do your research if you did not attend the lecture. Alright, so here I'm gonna tackle the 3 examples that I showed in class and the approach that I systematically should follow. And usually what I do is I get one student to try and analyze this and then try to come up with the MIPS version of it. So here it's in C, but it could be in any other high-level language, it doesn't really matter. So here we have an array. So one of the first questions to ask is, well, an array usually, does it fit? Usually, alright? Does it fit in a register, or should we store it somewhere else? Naturally, the answer would be we should store the array in the memory. Alright, so if we're gonna use the memory, so what kind of instructions do we dispose of? I mean, do we have in order to do that? Well, naturally it's the load and store, and in this case, because we are trying to read an element from that array and add it to another element and store it in a third element and a third variable here, so most definitely I'm gonna use the load instruction for that. If I'm loading from the memory, this means that I need to specify a base and an offset, and all the blah 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 we already talked about when we tackled memory. Question number 2. Here I'm getting element number 10. So if I'm starting with element number 0, I'm trying to get element number 10. So the question is, how if my base is 0, well, what would be the word offset in that case? So my element is 10 words away from my base. Fair enough? However, in MIPS, well, do we use word addressing or byte addressing? So you already know that answer. So I cannot use word addressing, so I'm using byte addressing. So the offset should be in byte, and we know that each word is 4 bytes. Hence, the offset should be 40. Fair enough? So this is how we get this element using the base and the address from the array, knowing where the base of the array, and apparently the base here I'm specifying it to be save register number 3. Right, so here I'm getting another element and putting the result in element. Should I get those in from memory, or would they fit in, let's say that they're integers, would they fit in any of the general purpose registers? Well, the answer is definitely a register. Why would I go to the memory, which is slower, if I can fit it in a register? Fair enough? So what would be the equivalent of that? First get the thing that I need and store it in a register from memory, and then add the 2 of them and put the result in a destination register. So let's see that. So this is what I'm doing. I'm loading my elements using the base and the offset, putting the result in T0 and temp register. So this is a load word here. Then I'm adding the element that I put in T0 to the element that I have in S2. So I suppose that S2 is representing Y here, and the result I'm putting it in S1, which is X. Fair enough? Right, so let's see a second example now. Right, so here we're seeing a condition, and we feel that there's two possible paths here. Path number one if the variables are equal, and path number two if they're not. So apparently there's some kind of branching that we'll have to do here, and we will see how to deal with that. So if let's analyze it for a second here. So check this out. If I'm doing some sequential instructions and then I find out that A is indeed equal to B, right? So I'm gonna put 1 to C. Should I continue and execute that one? Nope. So basically it would be nice to jump over that one, right? So keep that in mind for a second. So I can do a branch on equal, or I can do on branch if not equal. I personally use this one, but I mean any program can be coded differently. So this is my solution, doesn't mean that it's the only solution, correct solution out there. So I'm gonna use a branch not equal. So basically what I'm trying to say that if they're not equal, well, go ahead and give C 2, and if they're equal, go ahead and give it 1. So it's as if I'm replacing one of the equal here with a next exclamation mark, and then putting C equal to 2 here, and the other way around. Fair enough. So let's see what this gives in MIPS. So I'm branching not equal S3 and S4. So most definitely those are representing A and B. So I'm comparing A and B. Fair enough. A and B, and if they are not equal, I'm gonna go to the else. So I'm jumping if they're not equal. What if they are equal? Well, if they are equal, well, it will be normal to give 1 to C. So I'm putting 1, adding 1 to 0, and putting it in S1. So S1 is representing C here. Fair enough? Hold on, I don't have an initial value for 0 here. So what if I had 4 or something like that? Well, of course not, because the register 0 is hardwired to the value 0, so basically it will always be 0. This is the beauty of it. So hence I'm having 1 in C now. Now I want to see the case if they are equal. Am I done? If they are equal. So A is 1 and B is 1, so they are equal. So I should put 1 to C, and that's it. Should I do that? Nope. So I need to jump unconditionally to the end, or to done. What's missing now? Well, I didn't cover if they're not equal. So if they're not equal, I should go to the else. So now I need to have my else. Well, it's the same thing, but adding 2 this time and putting it to C. Am I done? Yes, I covered everything, all possible paths. So this is my done. We good? Right, so final example here. Check this out. So array, memory, loads and store for sure. Definitely load. Base and offset, awesome. K, variable, register for sure. I, variable, same time index. So it's a variable, so I'm gonna put it in a register. However, it will affect my index. So hold on, my index could be something that is moving. It's either the offset or something else. Alright, speaking of which, let me use the pen here because it's important. So if I want to move from one word to another, how many bytes am I moving? 4 bytes. Alright, so I need some kind of something. When my index moves once, right, I need actually to be able to move 4 times in the memory, because it's 4 bytes away. Remember, byte addressing. So I need to multiply that number with by 4, whatever that number is. So yep, the only easiest way to multiply, well, is to do a logical shift left. So shift left logical. So the whole point is, if I'm having this number, I'm moving once, I'm end up with that, so I'm multiplying by 2, binary. No, that's a 0. Right, if I'm moving twice, well, I'm multiplying by 4, binary. right? This is the whole point. So I'm going to use that one in order to be able to get to that from that. That's one. Second thing I want to use, again, this is my solution, doesn't mean that it's the only solution. You can implement it in a different way, and I strongly advise that you try an exercise implementing it in a different way. Pen. Check this out. If I fix my base here, so it's 0, each and every time I will move, my offset should move as well. So I will go from 0 to 4 to 8 to 12, etc., etc. Fixed base, variable offset. Alright, I don't want to do it that way. I want to do it in a different way. I want to make the base variable and fix the offset. So if each and every time I move the base once, well, my offset will be always 0. Get it? So it's one way or the other. Either fix the base and change the offset each time I move with my index, or just move the base with your index and fix the offset to be always 0. Let's see the result in MIPS. So shifting in order to get the 4 that I need. Fair enough. So there's my I. I'm shifting it. I'm putting it in T1. And my base, right, is at T6. So if at the very beginning I is 0, so my base is 0. So I'm adding 0 to 0, and I'm using that as the new base now. So this is the original base, and this is the new base that I got after I manipulated those. Well, if my base is moving, well, each and every time my offset will be 0. Get it? Each time my base will move here, change because of that, when I is incremented, right? My base will move, so my offset will be 0. And I'm putting the result of that word in T0. Then now all I need to do is compare it with K. And based on that comparison, I would know if I can continue here, incrementing I, or I just leave. So that's a branch. So I'm comparing K, which is represented by S5 here, to the content of my cell. And if they're not equal, well, I'm not going to increment. If they're equal, I'll go back to my loop. Alright, so I need to increment first, of course, and then go back to my loop. Fair enough? So see here, I incremented it by 1, S3 by 1, this is my I multiplied it by 4 in order to get the equivalent of it here, because it's byte addressing. Each time I move once, it means I'm moving 4 here. And then I'm shifting the base of my save, and then fixing, getting the word by fixing the offset, because the base is shifting, is moving. And then I'm doing my thing here. So that's it for the recap. See you soon.